Okay, here we are with another work solution to an AQA Physics A-level question in mechanics. Again, AQA continues its obsession with cyclists going up and down hills. If you haven't already read the question, please pause it and read it now. Okay, so the question is about cyclists going down a hill. They start from rest at the top of the hill. They reach a horizontal section of the road this is the horizontal section, at 16 meters per second. The mass of the cyclist and the bicycle is 68 kilograms. Step 1, calculate the kinetic energy of the cyclist and the cycle on reaching the horizontal section of the road. So 2 marks really for something very straightforward, simply half mv squared, sub numbers in. We know the mass of the cyclist is 68 with the cycle as well. The velocity they get at the bottom of the road was 16, so that's 16 squared. Sub numbers in, we get an answer of 8704 joules. Next step, the height difference between the top of the hill and the horizontal section of the road. So that's this height difference is 12 meters. Okay. Calculate the loss of gravitational potential energy of the cyclist and the cycle. So it doesn't matter which direction you go in. You can go straight down, or you can go at an angle down the hill. The loss in GP would be the same. So simply using our formula for MGH, for GPE, which is mass times gravity times height. Sub in our numbers, 68 times gravity, 9.81, times the height, which is 12. Calculate your answer. It comes out as 8004.96, but I'll round that to 8005 joules. Units are given in these, so I'm not writing down the units, but of course, always remember to check. Now the next step is the work done by the cyclist when pedalling down the hill is this. Account for the difference between the loss of GPE and the gain in kinetic energy. Right, so if they rolled down the hill and there was no friction, they'd start out with this much GPE, 8005 joules of GPE, and you'd expect them to have 8005 joules of kinetic energy. Okay? Now, they've actually come out with more than that. Why have they come out with more? Because they've also pedalled, converting some of their chemical energy into kinetic energy, right? But if you look at the total energy that was available, which is 8005 plus 2400 joules, it's greater than the kinetic energy that came out at the bottom. So in other words, it's like saying, I sent you to the shops with £20 and you've come back with a £5 gift card and £10. Where's the other £5? That's basically what it's kind of asking. I mean, they started out with this much GPE, they've put this much work in themselves, and you've only got this much out of it. Where's the rest gone? Well, the rest of the work has been done against friction, okay? Because the bicycle air resistance, the components within the bicycle all have frictional aspects to them. So I've written this out because my handwriting is terrible. So without frictional forces acting, the kinetic energy at the bottom of the hill would have been the total amount of energy supplied. So that's the GPE plus the work done by the cyclist comes out this, but only this was apparent, meaning that the total minus what was apparent must have been used doing work against friction. Now I think this would be enough to get you the 3 marks because it shows that you clearly understood what you've done. If you just wrote down the numbers and expected to get marks for that, you're not going to get them. You have to explicitly say why you're calculating what you're calculating and what you've done. Alright. Next step. The cyclist stops pedaling on reaching the horizontal section of the road and slows to a standstill 160 meters further along. Okay. Assume the deceleration is uniform. Calculate the time taken for the cyclist to travel this distance. So this is a SUVAT question, S-U-V-A-T. We've been told that it's 160 meters they travel. We've been told in the previous part of the question that they initially started at 16 meters per second. We've been told that they come to standstill, so that means that they get to 0 meters per second. We don't know the acceleration, but we do know it's uniform, and we don't know the time, and that's what we're looking for. So you break out your equation sheet, you look for the equation that has these terms and gives you this term, but doesn't have A because you don't have it. And if you have a good old look, you find S equals a half brackets, sorry, U plus V T. Okay, so we have S, we have U, V, and we want T. So just need to rearrange this for T. So get rid of the half by multiplying both sides by 2. So 2S, divide both sides by UV, divided by U plus V, should give me T. So 2 times 160 over U plus V, which is 16 plus 0, so that's just 16, gives me 20 seconds. Okay, 20 seconds is my answer. Alright. Now, the cyclist has rolled down the hill and is rolling along let's just draw him on. Rolling along from here, coming to rest and stopping, right, over a distance of 160 meters. Right? So, if they just stop pedaling, they come to rest because frictional forces are acting on them in this direction to slow them down. What is the average size of that force, right? So what to think about is they come down the hill here, they emerge with 8,704 joules of kinetic energy. So they've got 8,704 joules of KE. Okay? And as they roll along, they're doing work against friction, right? So whatever KE they had is going to be equal to the work they have done against friction, So 8,704 should be equal to the force times the distance, right? This distance is 160 meters, so that would be 160 meters, right? So rearranging would give me 8,704 divided by 160. So for an average frictional force of 54.4 newtons. Okay, so 54.4 newtons. Okay, I hope you found this useful. Please comment, subscribe, like and share. Thanks for watching.